Welcome to Etap webinar, Short Circuit and Dynamic Modeling of Inverter-based Resources. My name is Mohammed Zadeh. I'm a Senior Vice President of Protection and Control at Etap. In this webinar, first we look at the fundamentals of inverter operation and control. Then we look at the proper selection of Etap IBR models and tools. Look at the models like steady state for normal load flow studies, fault, quasi-dynamic, dynamic and transient model. We also look at the models from the perspective of the generic, standard, user-defined, and black box. We look at the tools that support inverter-based resources like load flow, short circuit, star and star Z, time domain load flow, transient stability, and co-simulation. As part of this discussion, we also look at our objectives, that what type of studies we do, whether it's a planning or grid impact study, whether we are designing or sizing assets, or whether we are doing grid code study or protection and control settings. And finally, I'll summarize this webinar. Inverters, or if you want to use a more technical term, voltage source converters, are devices that can convert the energy from, let's say, DC to the AC. Now, this is done typically by using switches. And as you see here in this figure, I have a two-level converter that converts the DC to the three-phase AC source, or three-phase AC form. Now, I've highlighted the letters VSC that stands for VSC that you've seen, but be careful that this is voltage sourced converter, means that is a converter that it's sourced, or it is fed by a DC form of energy, which is in this case a capacitor, or it can be a PV cell, or it can be a battery. Now, what the switches do, they kind of chop the DC and put it on the AC side. So as you see here on the right hand side, it kind of generates a pulse of DC voltages in the outside output terminals of the inverters. Now, it doesn't look instantly like a sine wave, but once we put some filters on the AC side, we can draw the fundamental frequency component that behaves more like the red waveform, which is our sinusoidal signal. Now, when we are looking at a inverter or voltage source converter, as we mentioned, there are switches that the pulses are fed typically through the pulse width modulation. And then there's a DC source, we talked about it, and we mentioned that there's always some sort of a filtering at the output side of the inverter to reduce the harmonics. Now, there is a series filter that typically is used to attenuate lower harmonics, and there's a shunt filter typically is used to attenuate higher harmonics. And then there's a step-up transformer that typically is Y-grounded delta, Y-grounded on the inverter side. This means that the inverter is not going to inject any zero sequence to network, but it can inject potentially positive and negative sequence. Older inverter technology inject only positive sequence, but newer technology also inject negative sequence as per recent grid codes. Also, there is a controller that kind of defines what quantities needs to be basically controlled. So typically it measures the current and voltage and controls the active or reactive power or voltage or power factor of inverter. Now, we are using this reference, which is a very good one, that's published in 2012. It's an IEEE transaction paper that reviews different power converters control in AC microgrid. So I recommend you guys to go through this paper if you want to learn more and get more details. Now, when it comes to the inverter, the way that inverter behaves significantly depends on the control logic and settings of the inverter. And in a higher level, inverter controls can be categorized into two categories: grid following or feeding, or grid forming. Okay, so for the sake of this webinar, I just use the term following not feeding. So grid following, grid forming. Grid following is an inverter that requires another voltage source in the system to operate, while grid forming can work independently without any source in the system. In grid following, we are always have a PLL that kind of tunes or sync to the grid to function. So it basically kind of measures the voltage, frequency, and that's the angle of the positive sequence voltage, and also built in it has also the frequency measurement, and it uses that to sync up and do the control. So if there is no voltage at the terminal, this type of inverter typically cannot function. Okay. Now, if I go to grid forming, there is no PLL. So we are kind of feeding the frequency to generate some artificial angle, and we use that angle to generate the sine wave and do the control. Okay, so it's just a comparison a little bit to understand what are the major differences. Now, when it comes to this kind of inverter grid following, what happens is that typically we are doing a PQ control, or it can be P and voltage or P and power factor. At the end, it comes to controlling the amount of Q. From a P and Q and voltage, we are using typically the clock transformer is used to decouple the active and reactive power control. So we come up with the active and reactive power, or DQ component of the current. So from that sense, we are trying to achieve a certain amount of current going out of the inverter. So from that perspective, inverter, which you can say is a PQ control, it's in reality is a current control. We control the current to achieve a certain P and Q, or we control the current to achieve a certain P and voltage, or we control the current to achieve a certain P, active power and power factor. So at the end, it's kind of from control perspective is a current control. Okay, we are controlling the current going out of the inverter. Typically the shunt filter is not part of the control. Okay, so the current that we inject, we control this current, and we control the power P and Q at this point. And this one is typically, if you are modeling it, we're modeling it externally. Okay. Now, typically the size of this shunt is also small. It has two purposes. One is for the reactive power control. One is for the if there's a need to meet the reactive power requirements of the grid, or you want to do, let's say, power factor correction. Also is used for attenuating higher harmonics. Now, when it comes to this controller, we're controlling the current, but keep in mind, inverter at the end, it's putting a voltage, DC voltage, that after filtering becomes AC. So there is a voltage drop across this reactor. That voltage drop, which is J omega L, so in time domain, it gets compensated here to achieve, to determine the voltage behind this inductor. So this UD and UQ are voltage behind this inductor that is fed to the PWM to determine basically the switching commands to do the pulses, okay? So from that perspective, let's understand this. When we are modeling this inverter, we are modeling it as a current source, okay? Now, how much is the current? You can have a simple transfer function to convert a P and Q to the amount of current. Or if you have a P and V to determine the amount of current from P and V. Keep in mind the current here is a complex number. It has a real and imaginary, or magnitude and angle. There is also a shunt, which this shunt represents basically the series, okay? And you can add also the shunt of this shunt filter as well here. But at the end, we are controlling the P and Q going out of the series filter here, okay? So if you want to model this CF, the CF actually needs to be connected to this bus too, okay? Now, when it comes to the strong system, when we are talking about integration of the renewables to the grid, especially typically we are connecting this into the middle of the lines or into the substations. We are connecting to the strong grid. So we are starting connecting to strong grid, and we are trying to control the current. What happens is that the role of this shunt becomes minimal. What does that mean? It means that grid is strong. Whatever you inject current, grid accepts that. But at the end, because you're controlling the P and Q that's going out of this bus, there is no difference to consider this Z or not. In reality, if you're considering it, we need to add V over Z to the calculation here to make sure that V over Z goes here, which is the current going through the C, and the rest goes to the system. Or we can completely ignore it from the current calculations and from the shunt, especially that happens typically in the software tools when they're connecting inverter to the grid. So it's kind of a current source only, is a voltage dependent or some sort of a power PQ dependent current source that goes to the system. Okay. Now, when it comes to grid forming, though, as you see here, that we typically control the frequency and voltage. So what we are trying to achieve is to have a certain magnitude of the voltage and angle and the frequency. And in order to do that, again, keep in mind, we are calculating the current. To a PI controller, we are calculating how much current needs to be injected to achieve the certain VD and VQ. But keep in mind, we're not saying exact fix the ID and IQ with the certain amount of P and Q, okay? But it's more, this is the V we want, we adjust the current till we get that amount of voltage. So from that perspective, it's easier to understand it as a voltage source plus impedance in series, like a Thevenin equivalent. And within the ratings or within the capability of the inverter, typically this is an ideal voltage source, means Z is almost zero, okay? But as you go outside the capability and ratings of the inverter, then this Z becomes variable and becomes a non-zero. From the circuit analysis perspective or phasor domain analysis, any Thevenin equivalent can be represented by Norton equivalent. So still it can be grid forming, can be represented by the current source, but keep in mind that grid formings are typically used in the VIC systems, in the microgrid applications, where, as we discussed also in the grid following, this Z becomes very important. Why? Because if you lose the grid or grid becomes weak and suddenly you're injecting certain current to the VIC system, voltage tend to rise. But in fact, because of this shunt impedance is going to damp those expected voltage rises, so voltage does not go beyond a certain level because of that. And that's more practical in the actual system. This inductor, it doesn't allow the current change suddenly, okay? Which means that it doesn't allow the voltage in the system to increase suddenly, okay? So there's a voltage source here, and if suddenly you lose the grid, there's a voltage drop here, okay? So what does that mean is that the voltage at the terminal doesn't go suddenly up or down, okay, to a very large value. As I mentioned, from the Etap perspective, from the phasor domain software analysis, we can model both of them with the current source. But it's important to know that when we are doing grid forming, there should be basically reference frequency and voltage as a set point. When it's a grid following, it's P and Q or P and V or P and power factor as a reference value. When we go to more like renewable power plant applications or larger scale renewables or IBRs, there's always a need for grid support. Means that IBR needs to, as per grid codes, to do some regulations to support the grid, either active power with respect to frequency or reactive power with respect to active power or with respect to the voltage. It sometimes needs to present some sort of a virtual inertia or virtual impedance. So there is a category of inverter control that's called grid supporting. Grid supporting falls between grid following and grid forming. Means that on top of this PQ, the PQ, you can have a, let's say, droop on P and omega on the frequency, and you can have a droop on reactive power as well. And the reason that we have this droop for reactive power that is not very common for generator, is more common with the IBRs, is that when we have IBRs within close, we are expecting more IBRs to be in close vicinity in the power plant. And if all of them want to react and all of them want to do a voltage control, the control going to fight each other, and there could be a control instability. So when it comes to the wind farms or solar farms with the energy storage, and there are lots of reactive power resources that are available. In order to make sure that there is a coordination and there is a contribution for all of them without a fight, there's always a droop, let's say, for the reactive power. We'll look at the more details in the next few slides. But you can create a grid supporting out of grid following or out of grid forming. Okay, very similar. They both of them support, but if your grid, you lose the grid, you cannot function as a grid supporting following. Okay, but with the grid forming, you can support that. Okay, you can still run as a microgrid or islanded system without a grid if you have a grid forming supporting inverter. Again, if you're interested in more details, please go to our reference paper that I gave you at the beginning of the webinar. Now, in the grid support, typically, there is a active power and frequency control. Means that if the frequency deviates from a nominal frequency, similar to generators, we want to have some sort of a droop to adjust the active power. Okay, if the frequency drops, you want to inject more active power. If increases, you want to inject less. Or if for the reactive power, we want to do the same with the voltage. If the voltage is within a certain range, we want to make sure that our power factor is 1. But if we have an over voltage or under voltage, we start basically absorbing or injecting reactive power system to bring the voltage back to the kind of a normal range. Okay. Now, in the distribution system application, in the microgrid application where the X/R ratios are low, what happens is that there is no one-to-one relationship between active power and frequency and reactive power and voltage, and these are not fully decoupled. So it seems that it's better also to have a power and voltage control. In PV curve, what typically happens is that if the voltage increases in the system, so if we experience an over voltage, we would like to reduce the power generations, let's say, to the system, or again, depends if you're charging or discharging. So we want to adjust the active power to make sure that it helps the system to tune the voltage to be close to the nominal value. So again, these are kind of a grid supports that needs to come on top of the basic control to make a inverter more like a grid friendly and grid supporting inverter. There is also a capability curve for inverter or for a plant as a whole. So we know that all the inverters are based on the switches, and these switches has very limited current rating, and it's not like a generator that can give 20-30 per unit current. It's very limited to around the nominal current, unless slightly maybe 20-30-50% above the rated value. Also, there's a limit on the DC bus voltage, DC bus voltage control, as well as if it has a WTG, you may have an internal voltage limit. So there's always a limit there. TSO typically has a certain requirements that, okay, you need to meet the certain capability, be able to inject or control this much active and reactive power. And they give you like this kind of shapes that you see on the right side. And many PV plants, let's say, have the regular capability like a red side, and in order to meet the grid code, either they need to install a certain amount of capacitor or a STATCOM, or maybe other reactive power resources. So one of the things that is very important to do is to be able to consider this capability and be able to do the study to determine that basically we can meet those requirements. Now, whatever we discussed so far was all about typically normal voltage range between 90 to 110%. When there is some disturbance, some dynamics, but not a major closed fault. Now, for the case of a closed fault, typically the grid codes have certain requirements. Again, these are for large IBRs, not for small ones or residential ones. There is a voltage right through, means that if the voltage drops less than, let's say, 90%, there's a curve that defines that how long the inverter or the IBR needs to minimum stay before tripping. or as well as how much reactive power needs to support, whether it's both positive sequence or negative sequence reactive power needs to be injected to the system. So again, this is called voltage right to, or VRT, capabilities that inverters typically in their control. They have a state machine that determines that now we are in the fault state or we are in the normal state. In the fault state, all these QV support and stuff goes away and we switch to a reactive power support during the fault. Once we go back to the normal, then again we come back to this type of controls of QV curve or PV control. Okay, so keep in mind that there's a dual behavior during the fault compared to during the normal condition. The same with the frequency deviation. If the frequency deviates, there's a range that within that range and time, this is a no trip zone, so inverter is not supposed, IBR is not supposed to trip. But as you also within this range, still the inverter or IBR needs to do some contribution by injecting or absorbing active power with respect to the frequency. Now, when it comes to the microgrid application or power plant control application, what happens is that most of the requirements that defined by grid codes are at the point of interconnection. Okay, so at the point of interconnection, the IBR, the system needs to meet, the plant needs to meet a certain requirements. Okay, so that's why when we do the study, we want to see that if the entire system as a whole, let's say for microgrid or power plant, meets a certain requirements. Now, what happens here is that we have a bunch of renewables and maybe energy storage and reactive power resources that they all supposed to work together. And in order to coordinate their behavior, in order to meet the requirement at the point of interconnection, there is a controller called power plant controller. In case of microgrid, there's a microgrid controller that they do active and reactive power, and they coordinate how much basically reactive power should come from, let's say, capacitor, from StatCom, from battery, from renewables. And when we do the modeling of an inverter in a plant or in a microgrid, it's very important to also model the power plant controller or microgrid controller. Sometimes certain functionalities like volt var compensation here that we showed, rather than being done at the inverter level, is done at the plant level. Again, it all comes to the expectation in terms of timings. If things are at the milliseconds level, typically they're done at the primary controller of the IBRs. But things at the seconds level and minutes level, they're all done at the power plant controller level. Okay, so when you're trying to do the study and modeling of a IBRs or a system including IBRs, you have to make sure that if it's working with a power plant controller or if it's working with the microgrid controller, you understand that what is the impact of those plant controllers or microgrid controllers and whether it's important to include them or not include them in the system. With that, I'm done with reviewing the fundamentals of the IBRs. And now we're switching to see what kind of models are offered by Etap for IBRs. The first model that we're going to look is the steady-state model that is good for load flow. So we have our classical inverter model as well as the smart inverter that's coming into the Etap 21. So let me just bring Etap and start showing it in Etap. So it's part of PV inverter or it's part of inverter, so you can use this smart inverter. The major difference between the smart inverter and regular inverter, first of all, you can select it here. So if you select swing or voltage control, megawatt control, power factor control, is going to be a classical inverter that we had for many years. And you can also select a smart inverter. When you select smart inverter, this is a smart inverter page will show up. The major difference between the smart inverter and regular inverter is that the classical inverter is like a generator. If you have a P and Q, it's going to have a fixed P and Q, or if you have a P versus voltage, it's going to have a fixed P versus volt and voltage set points, or P and power factor. But in a smart inverter, you have a curve that you define that how the reactive power should be with respect to voltage. Let's say this is a volt var control. Or if you want to do volt watt control, you can actually do the volt var control. You can go and define your curve for volt watt. okay, means that you want to curtail the renewable if there's an extra voltage on the system, or if you want to do watt and power factor control, okay? Again, rather than having a fixed voltage and power factor, you have a curve for it, okay? So you can adjust the power factor with respect to P at different values. So that makes a smart inverter in the first glance, okay? The second part of it is the priorities, whether you want to give priority to the Q or you want to give priority to the P value. Let's try to look at this with some example. So I have an inverter right now that is set to 1 megawatt generations. It has a 1 MVA rating as well, so no room for reactive power right now at this moment. And voltage of the analysis is also about 101. Okay, so I have about 101, and if you look at a smart inverter at 101 at here, there is no need of any reactive power injection. So things are good. Now, if I go to my OLV and increase the reduce the voltage of the utility, I'm gonna go here and bring the voltage to 90%. Okay, so again, there's something happening in the grid. There is a voltage drop, and the PV is supposed to contribute. So what you see here is two things. Number one is the because of the voltage drop, let me move this here. Because of the voltage drop, okay, to 93%, we're gonna have some reactive power. Because it's a Q priority, it's gonna inject Q. But because it has a limit, it's gonna bring down the active power. Okay, so it's going to curtail the active power, inject some renewable here. Okay, so if I go and say no, P is the priority, what's going to happen? If you run this, it's going to become all 1000, no reactive power, voltage 91%. But if you go and say no, I want to be more grid friendly, I want to inject more reactive power to the system, so you're going to go Q priority, and what's going to happen is that voltage becomes 93% because you're injecting some reactive power. You can go ahead, do your calculations that this is per curve, that this amount of percent generates that much Q. And you can do this also for the PV control or power factor control. And this is typically in the field that you have to see how your inverter works and pick the right control mode. And this is available for both the PV inverter and also the energy storage or the regular inverter, okay, that we have. Okay, now let's see what are the applications. If you are doing a planning or grid impact studies, you are trying to do the design and sizing, you want to look at the voltage profile, whether you need a capacitor, whether you need a StatCom, whether you need more reactive power resources in the system. If your voltage profiles are good, you can use a smart inverter if it's smart in your field, in your practice, and you can use the load flow analysis to figure out basically the effectiveness of the smart inverter to improve the system performance. Now, when it comes to the fault, now we have a short circuit model. Again, we are talking about a steady state performance. There is a fault, and what happens is that with IBRs, keep in mind, if your purpose of doing short circuit is to determine the circuit breaker rating, the bus ratings, the cable, keep in mind, IBRs typically inject probably the same as their nominal or a few percent more than their nominal, 20, 30, maximum 50 typically. They can inject current to the system, okay, unless you pay extra to do more, so they can inject more current, but typically is not that much. So if you're really trying to come up with the circuit breaker ratings or cable ratings, bus ratings, you don't need to do a big analysis. You need to avoid too much about the modeling of it. Okay, I'll show to you that with certain numbers, you can easily get that done. But when it comes to doing a protection study, especially when you're trying to do the directional protection, the angle difference between your voltage and current matters. And that angle is important, that how much reactive power you're injecting, whether you're active power priority or reactive power priority. There are many papers presented in the protection conferences showing that the directional protection failed for a power plant, failed for a microgrid because the inverters were on the real power priority, or they were on the power factor priority, and they're not behaving like a generator. Okay, so that was creating an issue. So when it comes to the short circuit, what we provide for the short circuit of the inverter is we have two curves. We have a general curve that represents the maximum current that can go through your switches. Okay, for now it's a positive sequence current injection, so phase current is the same as positive sequence. So your positive sequence is limited by this kind of curve. Now, if you say that my inverter is all 120%, you can go and put all of them 120%. That's it. So it's a fixed 120%. Okay, but if you say that no, my inverter, there are certain technology that if the voltage drops, there's a limitation on current injection, and this goes to a low value, to 40% or 50%. So what happens is that if you have a fault, the voltage is very low, inverter cannot give full 100% current because of the limitations on the typically DC side. Okay, now there is a reactive power priority, active power priority, and user-defined power factor. It's very important to select the right one. If you're dealing with the small inverter, residential, if this is not for a big plan, typically these are user-defined power factor or real power priority. Means that they do not contribute, they do not support the grid. But if you're dealing with the power plants that are in megawatts, if they're following grid codes, if they're supporting reactive power priority, means that you're using volt-var control. Okay, if you're using volt-var control, means that probably you're doing reactive current priority as well in your short circuit. If you are doing watt power factor, most probably you are not caring about being grid friendly, so you are probably here also user defined. So keep in mind that we kept them split, but because you never know, it's always two different controls. A short circuit and load flow or steady, or the normal conditions, are two kind of control within the inverter. So we kept them isolated so you can select them yourself. But typically when we are talking about larger scale inverters, when we are talking about megawatts and we want to do short circuit, typically we are at the volt-var, and typically we are doing a reactive power priority. Now, what happens in reactive power priority? We have a far right through curve. Means that if the positive sequence voltage drops, inverter puts more reactive current into, injects more reactive power to the system. If you have an over voltage somehow above 10%, you're going to absorb reactive power. Okay, again, you can go ahead and set your values here. I've set, let's say here 120%. Let me just in FRT also put 120%. Means that I can go full force reactive power control if it's needed. Okay, so now that I have my inverter set up for the short circuit, I can easily do the short circuit analysis. I can put the fault at the bus, or I can put at any fault location to do the analysis. So let me just go ahead and put the fault somewhere in the system. Okay, so I'm gonna go ahead here. I've created some kind of a dummy cable to place the fault. So if the fault is in front of an inverter, voltage drop to 0, it gives a full current. Most of the times you wanna analyze when the fault is on the system side and see the contributions, how the directional protection works and things like that. So if I put the fault here, if I go to my, let's say, short circuit analysis, I can go and place the fault here. So I'm using a StarZ module. I'm placing a fault here at this bus. It's a 3-phase fault. I'm putting a bus 2. So if I run the analysis, you see that voltage at this bus is 0, but as we go through the buses, voltages are increasing. And when I go to my inverter level, I see that voltage is about 41%. And if I just make sure that I'm just using the positive sequence component here, you see that you have great deal of reactive power control because voltage dropped to 40%. You're injecting quite a reactive current. This is -40, -90. Okay, so you see that there's a great deal of reactive power current as compared to the load flow condition that mostly we are injecting active power. Okay. So you can use this to determine the angle of the current. Okay, so right now you see that it's around minus 50, 70 something. If you put the faults at different location, you see that this angle can change. Okay, so if I go back and put kind of a sliding fault here on this cable, okay, and run this case, go inside and bring the slider. As you see here, that as I move the slider, you can see how the angles of the currents is moving, okay, and you can evaluate the performance of the IBR during the short circuit. Again, this is, you see that as I'm moving the slider, the current magnitude doesn't change that much typically, okay. What is changing typically is the angle between the voltage and current, and that matters mostly to the people who do the protection studies. Okay, so this is another important thing, is that when you're trying to do the study short circuit, what is your objective? Are you doing purely for the sake of short circuit analysis? Are you doing all to do the protection analysis? That defines how important are your settings, the curves that you're putting in your analysis. Okay, now when it comes to Etap, we consider the crowbar actions for the WTGs. So if you have a WTG, you want to see if the crowbar is active, how short circuit currents changing, so you can do that. We also consider the preloading condition for the IBRs, because their currents are within the range of their nominal currents or load flow currents, and then because of these priority things, power factor priority, we are always injecting the combination of the reactive and active power together. So it's important to consider that. Also, when it comes to the power plants with lots of IBRs, as we know that there is always a coordination with the power plant controller. They use some sort of a QV curve. And if you just do a pure current injection, just a random, like just a current injection based on the FR together, it may become a numerical unstable. So what we have done is we have done certain things to make sure it's numerically stable even for non-aggregated system and VIX system. Negative sequence current injection also is planned for Etap 22. So we looked at the steady state load flow, we look at the short circuit. Now, in many times we want to look at the profile of the wind or solar, and then play back those profiles and see the performance of our system. Okay, so we have a module called time domain analysis. So in the time domain analysis, we can always go to the module and define a time range where we want to do the load flow analysis. Okay, so in the time range, we actually define the profiles. These profiles for wind and solar, let's say, can come from a profile library that we provide. User can change them, store them, creates their own stuff. Okay, or if you have a profile that you want to read it from the file, you can define the location where you can go and get these basically the files. Okay, so in this case it's actually in the TDULF. So these are the files. So if you have an external file for your profile, you can show it here and use it as well to inject the data. Okay, it can be irradiance, wind, or PNQ directly. You can inject those values to the system. Okay, you can define which part of the data to read and consume. This is very important if you want to look at the voltage profile, look at your reactive power resources in the systems. But at the same time, what happened is that if you have a system with a bunch of IBRs, with a bunch of reactive power resources, and you have either power plant controller or microgrid controller, it's important to model those. So when you want to see the impact of those controllers on your renewables, we call this quasi-dynamic analysis. So basically in the time domain load flow analysis, there is a checkbox that if you check, the controllers, they're going to act and they're going to impact the assets. They're going to monitor them and they're going to command to them to do certain things as per the logics of the controller. Okay, so what we have done is In many applications, as I say, there's active reactive power control, there's an optimal dispatch, peak shaving, renewable smoothing. There are many things that typical microgrid controller or power plant controller do. And what we have done, we have introduced a new element in Etap 21 called controller. Controller can be used to model a generic or black box logic of a controller, and that controller can be a microgrid controller, it can be a power plant controller, it can be a generator controller, it can be even the tertiary control of ADMS or DERMS. Now, what is this controller element? Let me just show to you in Etap very quickly. If you go to the edit mode, in the instrumentation is the last icon, it's called controller. So if you drop one of these controllers to the system, let me just open one of them. You can always go to the DLL page and import a DLL. Now, where that DLL comes from, DLLs, we can, as an Etap, provide some DLLs, generic DLLs for battery, the same as UDMs. We provide some generic DLLs for battery, for maybe a microgrid controller, for a generator controller, PV controller. We also provide the actual microgrid controller or power plant controller that we offer to our customers. So this is a digital twin of our microgrid controller or power plant controller with full details, functionality of active power controller, which includes a rule-based, optimal dispatch, reactive power controllers, all the details, renewable smoothing, planned islanding, unplanned islandings. So all those functions comes here for the customers that acquire our microgrid controller or power plant controller. But at the same time, you see that it can behave as a different things. It also can be used for the vendors of the IBRs. So vendors of the IBRs can use this to generate a black box model for their inverters, for their IBRs. So we have a slide that will talk in details about that. In reality, this controller element is a DLL interface where users, which can be you as a customer, or it can be we as a Etap engineers who do modelings and analysis, or can be a vendor of an IBR, get this controller DLL interface and develop their own control logic and settings, where once you import it in Etap or controller element, then user can start setting the controller, run the analysis, and interface it to the components in the model. Okay, it's a C# interface, but can wrap any 64-bit native DLL, like based on the C++ or Fortran. So if you want to use those to do a black box model, you're more than welcome. The control element is handled right now in time domain load flow, and transient stability is a time domain type of component. It can do primary, secondary, and tertiary control in transient stability. It can do secondary and tertiary control in the time domain load flow. Time domain load flow runs as small as 1 second right now. So if you want to do really primary control, you cannot do a 1 second. You have to go to millisecond level to be able to do primary control. But secondary control and tertiary control you can do, which is very important, which is mostly the practice to do power plant control and microgrid application. Again, we talked about it. It can be a generic, standard, or black box model. Also, it represents the digital twin of Etap model. Let's go to Etap. I'm going to time domain analysis. I'm going to run 24 hours from January 1st midnight to January 2nd 1 a.m. 25 hours with a resolution of 1 minute. I am going to run this analysis, which is about 25 hours 1 minute, 1501 cases we are going to run. So what's going to happen is that if you run this, there is a generation, there is a load, and at certain point in time there's an excess of power from generations, then load, so we are exporting to the grid. And the job of the microgrid controller is to command basically a battery to charge at those times, and also at certain points you are importing lots of power from the grid, so it does a peak shaving. So I try to just demonstrate that simple case for now. Again, we are running 25 hours of simulation. So let me start that. So this takes about, I think, 2 minutes to run. And within that 2 minutes that it's running, I'm going to wait and come back to just save time. Okay, as you see, it took about 2 minutes to run this analysis. And it's done. So what I'm going to do, I'm going to go ahead first, plot the power transformer. Not the power, the PV transformer. You see that I have a profile for my two PVs here. Okay, they're pretty similar. I'm going to go about 2 megawatt of the generation. Now I'm going to also go ahead and plot my AC cable, the tie cable to the grid. So as you see here, let's also plot the load. There you go. So I have all three graphs. As you see, as my generation increases, okay, here, at certain point I have 2 megawatt, which is more than my load. So what happens is that my in my microgrid controller is going to command my batteries. So if I bring my battery 1 and battery 2, power is going to command those batteries to charge. So we are charging, okay? We start charging, and then the moment that the load drops, okay, or sorry, the load increases, okay, so we get a load increase here, and your renewable drops, what's going to happen is that it's going to command to discharge to actually cut certain amount of power here, okay? So it does the peak shaving. So you see now the controller in action in the quasi-dynamic analysis. That is commanding your battery to charge, to discharge, to do the peak shaving, to do the POI control. It can also do reactive power control, plan islanding, and all those kind of things that I'm not going to go through it at this moment. But if your purpose is to see the peak shaving analysis, if you are trying to do the battery sizing, if you are trying to do the reactive power sizing for a plant, for a microgrid, for a power plant, that's the tool that you need to use. That's your time domain load flow to do the quasi-dynamic analysis with the controllers. You have a controllers for your microgrid controller that does that. So if your ADMS sends some command to curtail a certain amount of power, you can again use controller to do that. It has certain functionality here that you can use it to actually command to do plan islanding or things like that for a microgrid application. Now let's get back to the presentation. When it comes to the dynamics, means running transient stability, Etap offers abundant amount of model, generic, standards, VEC models, European models, WTG type 3, type 4, the UDMs based on different IC standards, based on the VEC models, RAPC models, plan level controller, and then the models for the battery, generic models based on the VEC 2014, and some older models that we received through, we've done it for our customers before. There is a link I provided here, is the webinar, Stability Studies for Power System with DR. So if you're interested to know a little bit more details about these UDMs, we offered a little bit more details review in that webinar, so you can find that information. As well as you can go to our website regarding the dynamic models in Etap. There are lots of information about this model. You can always go to Etap and open a model, and let's say if you put a WTG and you go to the UDM, let me just quickly do for you one here. You can go to WTG, you can go, let's say, to the model here. Let's say for type 4, we have a UDM model, we have a VEC model. If you're interested in the UDM model, you can always go to the UDM editor here, and let's say pick one of these. You can have a VEC second generation type 4 8B. So that model is available in the UDM, so you can take a look at that. Again, when it comes to the transient stability studies, you need to also figure out that which model is the right model to use, okay? But keep in mind that most of these models that I just mentioned here for you, these dynamic models that I mentioned to the UDM built in, these are typically the models developed by the grid entities that are more interested in the impact of renewables in the large grid. So they're good for planning a study, for grid impact studies, for some feasibility studies. But if you're interested to see the coordination of certain control within your plant, if you're interested to study your plant or do a grid code studies that you look at your basically spatial dynamic performance of a certain IBR during the voltage drop, you cannot use a generic model or standard model. You have to use a vendor-specific model. Again, either the entity who requests you to do this study defines that whether it's acceptable to use a generic model, standard model, or you have to use a black box model. But if you're okay to use a generic model, if you're doing feasibility, some designs where the models aren't available, you have lots of models. Go to that webinar and get more detailed information about that. I've also here listed that if you're doing certain feasibility studies, design studies without a black box, when it's not available, vendor not selected, you can use those type of models. Now, if you are doing grid interconnection studies where you need to do voltage right through, frequency right through, you need to verify that a certain vendor IBR meets the requirement, grid code requirements, you need to use a black box model. Okay, so we provide a package for the vendors. So if you're using Etap and you know your vendor, you can communicate with vendor, we provide this package. And what this package does is that it has a mechanism that allows the vendors that if they have existing model that's done for other tools or for their other purposes, they can easily wrap that within a DLL and use it within Etap controller DLL. And be able to use it within simulation, transient stability simulation. Okay, typically when we are doing with a vendor specific model, we are running transient stability simulation, and we have a very nice package that we provide to the vendors that they can use it to develop a black box model. So they can do the positive sequence modeling within transient stability. To the vendors, they also provide a version that does all sequence as well if they're interested. But in the Etap 22, we also officially released the transient stability with all the sequences. Now, sometimes the vendor does not provide a black box model, but they maybe have a EMT model, like a PSCAD model. We also provide a co-simulation with PSCAD. Okay, so if your report expects to do an EMT analysis, even the transient stability or positive sequence transient stability is not acceptable, and you have to do an EMT analysis, so your solution can be a co-simulations. So most of your system is in the Etap and your IBRs located in the PSCAD. So if you're interested at how we do the co-simulation, please refer to the EMT co-simulations webinar. If you just search through the Etap webinars, I think I've provided a link here. There you go. If you just Google Etap and webinars, it takes you to the link where you can see the recording. So we have if you select on view all the webinars, okay, we have EMT, that's one of the simulations. One of the webinars. We also have the stability studies for the power system with DRs. If you're interested in power plant controller, there's a webinar for power plant controller, and also there's a webinar on also a co-simulations of electromagnetic and phasors. One more thing that is very important as people start to do a microgrid type of simulations where they're supposed to do grid forming. As I mentioned, it's very important to model that shunt Norton equivalent for the series inductor filter for the inverter. It's also very important if you are doing it for the weak interconnections. There are certain application industry we have seen that have weak interconnection. They're trying to do a transient stability analysis, and if they just purely use a current injection models, it's going to fail. And you need to have this series kind of Norton equivalent. With this, let's summarize this webinar. First, we talk about the fundamentals of inverter operation and control. And this is very important that for whoever is trying to do system studies with inverter-based resources, it's important to understand how they operate, how they're controlled, And for different type of systems or IBRs, what type of models are available and what each model do, what are the different analysis tools, to make sure that that knowledge of how inverter operates can help them to select a proper model and proper analysis tool. We talked about Etap models for IBRs, and we also talked about at the same time the proper selection of the models and analysis tool to meet study objectives. We are offering a smart inverter model for the steady state and load flow and time domain load flow analysis in Etap 21, as well as we have a controller element and quasi-dynamic simulation that allows the user to model supervisory and tertiary control for microgrid control, power plant control, along with the IBR models to work together, interact together to be able to study and do designs and sizings of the IBRs, of the energy storage or reactive power resources in the system. We quickly went through the dynamic models. There are different types of dynamic models are available. We talked about the built-in models, the UDM models, as well as we talked about having a vendor DLL, that if the vendor provides a black box model for Etap, the users can take benefit of that, as well as a code simulation. We just mentioned about it, that there is a webinar that you can go and take a look at that. So with that, I'm done with this presentation. Thank you.